Okay, so we've got 3 sections to do today. 2 of them are pretty short, and if we don't get all the way through the 3rd one, it won't be the worst thing in the world. We'll finish it up next week. So first section is section 7.3. And if you remember last time, we started talking about radicals and radical expressions and what is a radical communicating to us and what do we do with it. So in 7.3, what we're going to talk about is different ways to simplify radicals. So we're talking about simplifying radicals in this section. So there are 2 properties of radicals that end up being useful to us in order to simplify. So the first property of radicals is called the product rule. What the product rule of radicals says is this. And I'm just going to write this down for square roots, but this works for any radical, cube roots, 4th roots, 5th roots, whatever. It says if you have a square root of a first number, if you have a radical first number, times a radical of a second number, as long as the indexes are the same, I've got 2's on both of these. These are both square roots. As long as the indexes are the same, then what you can do is you can multiply what's under the radicals. So we can have the root of a times b. So that works in both directions. It means if we have 2 things under the radical being multiplied, we can think about them separately also. And so both of those are going to be useful to us. So first thing we're going to do is we're going to apply the product rule with separate radicals just to get used to it. And if you have any questions about it, so for instance, if I have the square root of 5 times the square root of 7, so the square root of 5 times the square root of 7, well, according to the product rule, what do you think that is going to be equal to? It's going to be the square root of, you still need the radical, of 5 times 7 is 35. Okay, you can multiply both things and put it under a single radical. So I have a few examples that you're going to do of just this same thing. That's as complicated as the product rule is going to get for us. Okay, so here's we'll just go one at a time. Here's a first example for you. So I'm going to just give you 15 or 20 seconds. Write down what you think the answer to the square root of 7 times the square root of 11 is. And what did you write down? Square root of 7 times the square root of 11 is square root. Okay, we still need our square root. 7 times 11 is 77. Anybody got a question or concern? Here's another one. I'd like you to do the cube root of 4x times the cube root of 5y. All right, the indexes on both these radicals are the same. So my answer is going to be a cube root. And what's going to be under my cube root? What's 4x times 5y? What's 4 times 5? 20, and then xy. There you go, 20xy or 20yx, the order of the letters. I just go alphabetical, but it's not super important. All right, one more product rule problem. This problem has things outside the radical too. So I've got 2 times the square root of 3 times 6 times the square root of 5. And the reason I give this example is just for the following. When you have things both outside and under the radical, you don't cross over. You multiply stuff outside the radical with other stuff outside. You multiply stuff under the radical by the other stuff under. So go ahead and give you 15 seconds. Propose what you think the answer to that is. Okay, what do I get when I multiply the stuff outside the radical? So 2 times 6 is 12 indeed. And then you multiply the stuff under the radicals. Square root of 3, square root of 5 is square root of 15. You don't cross over. The radical is like a force field. Okay, so you can't just multiply the 12 times the 15 at that point. Any questions? All right, well then that's the product rule. That's our first one. The second property of radicals that allows us to simplify is called the quotient rule. So this is the only 2 bits of new information in this section. We just applied the product rule. We're going to come back to it in just a minute. The quotient rule says something similar, except with division. It says if I have a radical of a first thing A divided by a radical of a second thing B, then what I can do is, since they're both under the same index radical, I can just do the radical of A over B. And also this has use going backwards. In fact, we've already used the quotient rule. We just did not realize it because I didn't say that we were using it. If you remember last time, I think all of you were here last time, in class, we did this problem when we were talking about radicals and we were introducing them. It was something like the square root of 49 over 36. And if you remember at the time, I said, well, with radicals, you can consider the numerator and the denominator separately. And that's all the quotient rule is saying here. It's saying if you have a fraction under the radical and going this way, then you can consider the top and the bottom independently. And vice versa. If you have 2 numbers that you could divide them, then you can do that. You can do the division first and then the radical second. Okay, so the order doesn't matter. So we didn't write this down. I don't expect you to write this down, but I just want to show you how the quotient rule applies to this. We could say, okay, square root of 49 over 36 is the same thing as the square root of 49 on the top and the square root of 36 in the bottom. I'm considering the numerator and the denominator independently. And then what times itself gives me 49? Indeed. What times itself gives me 36? There you go. And so we did that last time, so that the quotient rule is not necessarily new. So the new way that we'll apply it is this. If I have the square root of 7 over 25, the thing is, while 7 has a square root, it doesn't have a nice whole number square root. Okay, there's no whole number times itself. The square root of 7 is some sort of non-ending decimal times itself, so it's a little harder to write down. So for that reason, I'm not going to worry about the square root of 7. I'm going to leave it. So the numerator I leave as it is, the square root of 7. The denominator is the square root of 25. Now 25 has a nice whole number square root. What times itself gives you 25? 5. So we did not take the square root of 7. The radical remains in the numerator. We did take the square root of 5, so there's no more radical in the denominator. Okay, that was one of the things that I stressed last time, is once you perform the operation, that the radical goes away. Okay, so no more radical in the denominator of this. So I'm just going to write down 3 problems for you to do the same sort of thing. So your first one, just go ahead and do the square root of 81 over 100, and then the square root of 3 over 121, and then the 4th root of t over 16. Use the quotient rule for each of those to evaluate them. All right, so the first one, the square root of 81 over 100. Again, I'm just going to write this down to show you how we are applying the quotient rule. You did not have to write this down, but the quotient rule says, okay, I've got that fraction under the radical. That's the square root of 81 over the square root of 100. Square root of 81, I hope you wrote down 9. The square root of 100 is 10. Again, remember, once you take the root, the radical goes away. There's no more radical on either of these. 9 over 10 is the correct answer. This one right here is the square root of 3 over the square root of 121. Well, 3 is 3 times 1. It does not have a number, nice whole number times itself. So we'll leave the square root of 3 just as it is. But 121, if you mess around with your calculator for a moment, what times itself gives you 121? The denominator has no more radical because we took the root. This time I just changed it to a fourth root. So we've got the fourth root of t in the top, the fourth root of 16 in the bottom, and then once again the fourth root of t, I don't even know what to do with that, so that's just the fourth root of t. And then what times itself 4 times gives you 16, and that's going to be 2 times 2 times 2. So these are our 2 basic rules. The product rule dealt with multiplying radicals, quotient rule dividing radicals. So everything else we do today, the rest of this section, and then however much of the other 2 that follow, everything else today is going to involve the quotient rule and the product rule. Okay, so that's why I grouped these sections all into one day, is because they're all just kind of an extension of practicing the same thing. So the next thing we're going to do here with the product rule, this is maybe the most important thing of the day. So here's what I'm going to ask you to do. I'm going to ask you to simplify, and we've got this, the square root of 20. I will tell you, this is super important, especially if you're going to college algebra. We just used this. I have a college algebra class just before you all, and we just used this ability to use the product rule to simplify a radical today a bunch of times. We were talking about circles and the radius of circles, and using this ability to simplify square roots reared its head today. So notice though, 20 does not have a perfect whole number times itself, right? 4 times 4 is 16, 5 times 5 is 25, and 20 is in between those 2 numbers, 4s and 5s. Okay, so there's not a perfect one whole number times itself. But what we can do, okay, is we can take this radical and we can, it's kind of like reducing a fraction. We could simplify it. So what you want to do, okay, this is your goal. Anytime I ask you to simplify a radical, you want to ask yourself, is there a factor of this number? Is there a factor of 20? That is a perfect square. And just in case you've forgotten or you didn't catch on, perfect squares, I mean, your calculator can tell you this. These are the numbers that you're concerned about. 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, 6 times 6 is 36, 7 times 7 is 49, 8 times 8 is 64, 9 times 9 is 81, 10 times 10 is 100, and you can keep going. I probably bored you long before I got to the bottom of that list. But what you're looking for is there a number on this list, and we could keep going, that is a factor of this? So, what do you say? Is there a factor of 20 that is on that list? 4. 20 is 4 times 5. And you might be saying to yourself, Kirkster, that's great, but could I have used 2 times 10? And the answer is no. Okay? You have to pick a number that is a perfect square. Otherwise, this simplifying process does not work. Now, this next step I'm going to write for our first few problems, but my hope is that once you get used to doing this, you can skip from here to the final answer. Okay, but I don't want to skip right now because I don't want to unintentionally lead to any confusion. We just talked about the product rule of radicals. The product rule of radicals says when you multiply something, you can consider each of these things separately. So I can consider this as the square root of 4 times the square root of 5. So I'm going to write this the first few times. I would encourage you to write this the first few times, just so you know what is going on with the process. But then here's the end result. What's the square root of 4? 2. No more radical. Once you take the radical, the symbol goes away. So the square root of 4 is 2. It is now outside the radical. There's no more. Square root of 5 is an irrational number. It's 2.1 something, and it goes on forever. I don't care about that. I'm going to leave it exact square root of 5. So 2, this 2 is outside the radical because we couldn't take the square root of 4. The 5 stays under the radical because we could not find a whole number that times itself gives me 5. You tracking with me on this? It's probably the most important thing we're going to do today, okay, is this. So make sure that if you have a question, you let me know. Here's one for you. Nice, relaxing example. Same sort of thing, square root of 45. Simplify that, please. If you're not great with your multiplication table, again, just take that number 45 and divide it successively by each of these and see which one goes into it. And that's the process. Is there a factor of 45 that is on that list right there? 9, perfect. 45 is 9 times 5. Again, I'm intentional here. I know 45 is 3 times 15. That would work too to give you 45. But the problem is 3 times 15, neither one of those numbers has a square root for me. So 9 is a perfect square. That's why I like this one. And so the product rule of radicals says I can now give them each their own house. And so I do that. The square root of 9 is 3. No more radical on the 3. It's outside. The square root of 5 I can't do, so it stays under the radical. So I have one number outside. I have one number underneath. And that's my answer. We're doing okay. We're going to practice a few more times. Okay. And then this, if you can do this, then the very next section we do, which is section 7.4, there's absolutely no new information. It's just applying this as part of another problem. That is it. Okay, so you kind of get a whole section for free if you can do this. So ask me whatever question you need to, because there's going to be a bunch of these on the test. So here's another one for you. I would like you to do this. What is the square root of 50? If you would simplify that for me, please. Okay, does 50 have a factor that's on the list? What is it? 25. 50 is 25 times 2. Okay, so when you try your factors, you get down to 25. 50 divided by 25 gives you 2. There it is. And so product rule of radicals says I can simplify this into the square root of 25 times the square root of 2. The square root of 25, that does have a nice whole number square root. That's 5. Square root of 2 does not, so it stays square root of 2. You don't do anything with that part. Okay, I've got one more square root problem that we're going to do, and then we're going to also apply this to cube roots. Same process, different list of numbers. I'll write up the perfect cubes for you. But here we go. I would like you to do the square root of 24. So what is the perfect square factor of 24? Yep. You don't want to use 8 times 3. You don't want to use 12 times 2 because that doesn't do you any good. You need to factor this into something that's a perfect square. Product rule of radicals says that I can separate this now. Square root of 4 is 2. Square root of 6 does not have a nice clean square root, so I leave it under the radical. So we can do the same thing with the cubes. So for instance, if I change this problem just a little bit and say instead of square root of 24, let's simplify the cube root of 24. Well, now my process is the same with one little twist. Pardon me. Instead of looking for a number that's a perfect square under the radical, I'm going to look for a number that's a perfect cube under the radical. So you're just looking for a different list of numbers. So the perfect cubes, in case perfect cubes, 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. 5 times 5 times 5 is 125, and they get larger very quick. 6 times 6 times 6, I don't really know what that is. It's 216. And then you can keep going, 7 times 7 times 7, 8 times 8 times 8, 9 times. I'm going to stop the list there because I'm running out of mental capacity. Now the question is, since I'm looking at cube roots, is there a factor of 24? Is there a factor of 24 that's on this list now? Yeah, 8. So I use the cube root of 24 is 8 times 3. You might be thinking, Perkster, you just said not to use 8 a minute ago. You said 8 was not good. It's a great question. I'm glad you're processing it. 8 was not good when it was a square root. When it was a square root, I had to pick a number that was a perfect square, 4. Now that I'm doing a cube root, I've changed the index. I need a number that is now a perfect cube. Same process, same thought process, just a different number. So this becomes the cube root of 8 times the cube root of 3. The cube root of 8, what times itself 3 times gives you 8? That's 2. And then cube root of 3. There we go. Again, I can't take the cube root of 3. There's no nice whole number answer to that. So I'm just going to give you one perfect cube to do. Give this your best shot. Use your calculator to figure out what number would divide in. Just do the cube root of 54, please. All right, is there a factor of 54 that is on this list right here? Yep, if you use your calculator, 54 divided by 8 doesn't work. 54 divided by 27, oh, that works. 54 is 27 times 2. So product rule of radicals says I can take the cube root of 27, I can take the cube root of 2, I can consider them separately. Cube root of 27, what number times itself 3 times gives me 27, that's 3. What's the cube root of 2? Well, it doesn't have one. Well, it has one, but it's not a whole number, so we are going to leave it just like that. All right, we're almost done with this section. Okay, that's super important. Being able to simplify radicals. If you can catch on to this, if you can practice it, that will pay dividends for you when you get to the next class, college algebra. First day of college algebra class, if you have me or you have whoever you have, the very first section of that class will involve simplifying radicals. Okay, so if you catch on to it now, it's going to help you immensely. Okay, so what we have not talked about as far as simplifying our radicals is what happens if there's a variable under there. So just going to give some examples, and you're going to help me follow this pattern. Okay, so square root of x squared. What times itself will give you x squared? True. X times x will give you x squared. That's great. How about this? The square root of x to the 4th. Perfect. Because you are remembering the rule for my exponents. When I multiply x squared times x squared, 2 plus 2 gives me 4. You add your exponents. So 2 plus 2. Here's another one. X to the 6th. What's the square root of x to the 6th? What times itself is x to the 6th? Third, yes, because 3 plus 3, we add the exponents when we multiply. 3 plus 3 gives me 6. One more, and then you're going to help me see the pattern here. Okay, one more. So square root of x to the 10th power. Square root of x to the 10th power. What times itself is going to give you x to the 10th? Perfect. Thank you very much. You're doing great. 5 plus 5 is 10. So after you've written all those down, can anyone recognize what the pattern is? What have we done to the power every time in order to take the square root? It's half. Yeah. So to take the square root, it is 1/2 the power. Perfect. So now knowing that, I've got 2 problems that I want you to do. I want you to do both of these square root problems. So the first one is the square root of x to the 20th power. And the second one is the square root of x to the 18th, y to the 30th. Take the square root of both of those with those powers. Okay, following the pattern, when I take the square root of something to a power, I take half the power. So what's the square root of x to the 20th? That's going to give me half of 20 is 10, x to the 10th. Great. This one, product rule of radicals, says I can consider them each separately. So my square root of x to the 18th, square root of x to the 18th is going to be what? Perfect. X to the 9th, half of 18 is 9. And the square root of y to the 30th is y to the, perfect. You're doing a great job, half the power. Okay, pretty much the last thing from the section then is this. That seems to work great when my powers are even, right? 2, 4, 6, 10, 20, 18, 30, all those are powers even. What happens then if I ask you, what is the square root of x to the 11th power? Well, one thing you could do is say, okay, well, 11 divided by 2 is 5.5. Bam, we're done. But we want to avoid decimals in the exponent, okay, when we're dealing with our variables. So here's what we're going to do. This is again is the pattern. We know how to take the square root when the power is even. So what I'm going to invite you to do is this. Whenever you have an odd exponent, Whenever you have an odd exponent, just pull the odd one out. So when I take one of the x's out, I'm going to put times x. When I take one of the x's out, how many are left? Whoops, I'll do a better job there. So x to the 11th is x to the 10th times x to the 1st. 10 plus 1 is 11. So I've done the same thing here that we were just doing with the numbers a few minutes ago. I've now split this up. I have one thing I can take the square root of. I have the other thing that I can't. So product rule of radicals says I can consider these things separately. Square root of x to the 10th is, it's right over there, half the power, x to the 5th. Square root of x, I don't know what x is. It has no power. So I'm going to leave it under the radicals, square root of x. So I've got two of these that you're going to do. And then there's one little thing that you've probably seen 1,000 times in your math life before, but it's part of this section, so I need to remind you of it. So here we go. First, I would like you to do this. What's the square root of y to the 17th power? All right, under the radical, when I pull the odd y out, how many y's are left? Right? Product rule of radicals says I can consider each of these things separately now. What's the square root of y to the 16th? Perfect. 8, half the power. Love it. Well done. Half of 16 is 8, and then square root of y. All right, one more of these, then you're just about finished with this one. And the last problem for us is the square root of, let's say, x to the 27th power. One more time, I'm going to pull the odd x out. When I do that, when I take one of these x's away, I'm left with x to the 26th. The product rule of radicals says I can consider each of those things as a separate entity. So the square root of x to the 26th, when I take half the power, that's x to the 13th, and then square root of x. I've taken the square root of this, so it's outside the radical. I haven't taken the square root of that, so it stays under the radical. One final thing from this section involves groups, and that's why it is in this section. It is what's called the Pythagorean relationship. I'm guessing you've probably seen this at some point, middle school, high school, in some math class you took or geometry. What the Pythagorean theorem says is this, is if you have in front of you a right triangle. Now, in case you haven't seen the Pythagorean theorem, I don't want to assume too much. Okay, a right triangle is a triangle that has a right angle, meaning a 90-degree angle. Like the floor and the wall should be at 90 degrees, hopefully. Okay, so that's what a right angle is. If you have a triangle that has a right angle, then there is a cute little relationship between the three sides of the triangle. In fact, if you continue in your math life and you take trigonometry, there's a generalized Pythagorean theorem. There's a relationship between the three sides of any triangle. That's a little more complicated when it's not a right angle. So Traditionally, the letters to represent the sides of a right triangle are for the two legs, A and B. So these sides here that surround the right angle, these are called the legs of the triangle. And then this longer side right here that goes across the right angle, this is called the hypotenuse, which I just recently learned how to spell. So I'm 50 years old. I think it took me 49 years to learn how to spell this. So there we go. There's an E in there. That's what always got me. Hypotenuse. So A and B are traditionally used for the legs. C is traditionally used for the hypotenuse. And here's the relationship. This is the payoff. And what the Pythagorean theorem says is if I square A and then I square B and add those two things together, then that's equal to the square of the hypotenuse, the square of C. And that will always work for any right triangle. So we're each going to do one of these problems to finish out our time in this section because figuring out the value of a side does involve the square root. So here's my problem right here. I'm going to have this right triangle. I'm going to label the sides 6 and 4 and x. So I'm looking for the hypotenuse on this problem. I'll give you a moment to write that down. Then you're going to help me set up the Pythagorean relationship. All right, well, tell me, what's one of the legs squared? What do I get? 2. So 4 squared is 16. And then I heard both of them. The other one, 6 squared, is going to be 36. We'll take it one step at a time. So the first leg is 4, 4 squared is 16. The second leg is 6, 6 squared is 36. And then I'm looking for the hypotenuse, that is x, so x squared. Now you go into your calculator. 4 squared is 16. 6 squared is 36. X squared. 16 and 36, that is 40, that's 52. Here is where, or here's the reason this problem is in this section, is because of this. If this says x squared is 52, but I need to figure out what x is, then what that means I need to do to both sides of this is I need to take the square root of both sides. You just answered this question a moment ago. The square root of x squared is x. There we go. I've got my side that I don't know. The square root of 52, well, I don't know. That is not a perfect square. So then I would ask myself, does 52 have a factor that's a perfect square? And the answer, if you grab your calculator and you just start trying at the top of the perfect square list, 52 divided by 4, oh, that one works. 52 is 4 times 13. So last step, the square root of 4, I can do that. The square root of 4 is 2. That's the product rule of radicals. The square root of 13, I can't do. It stays the square root of 13. That's the missing side of that triangle. So I'm going to have you do one, and then we're going to shut it down for this section right here. So here's your right triangle. Right triangle. So your sides are these. You've got x over here. You've got 5. You've got 8. So set up the Pythagorean relationship. Do your best to solve, and we'll see how you do. right, so I'm going to set up the relationship here. If you got different numbers than me, let me know so we can compare results. So I'm going to do my legs first. So it doesn't matter what order. My first leg is 5, so 5 squared. My second leg is 8, so 8 squared. And the hypotenuse is x, so x squared. 25 squared, excuse me, 5 squared is 25. 8 squared is 64. 25 plus 64, 2 and 8, that's 2 and 6, that's 89. And as far as I can tell, when I go to take the square root of both sides, I think 89 does not have a perfect square factor, or am I wrong on that? Did anyone find a did you go down the list? No perfect square factor? I don't think it does. So I'm going to say that the answer then is just going to stay square root of 89. Okay, there's no number on the perfect square list that divides evenly into 89. So that's it. I'm done with that problem. All right, give those problems a try. Email me over your weekend. I know